Hi everybody, we're going to do some equations today from Stewart Calculus, Early Transcendental 7th edition. We're going to go ahead and be doing equations from 11.7, question number 9. And this is asking us, test the series for convergence or divergence. And if you're already in this section, you should have already been familiarized with these series tests. This is the basic order that the book suggests we should use in order to decipher whether this series is convergent or divergent. So we'll go ahead and apply the first test, the p-series test, which basically states that if the equation that we are using, k squared over e to the k, if that equation is raised to p and p is less than 1, then the series is convergent. But if p is greater than 1, the series is divergent. But since here we have in the denominator e to some variable, we can't apply the p-series test. So you just go ahead and cross that off. The next test we'll use is a test for divergence, which basically states that if the limit as n approaches infinity, a sub n does not equal 0, then the equation is divergent. So we can go ahead and apply this test to see if the series is divergent. So we're going to take the limit as k approaches infinity of k squared over e to the k. And plugging infinity into this equation, we get the indeterminate form of infinity over infinity. We can go ahead and use L'Hopital's, which is basically we're just going to take the derivative of the top and the derivative of the bottom separately. So the derivative of k squared is 2k. The derivative of e to the k is simply e to the k. And again, we get the same indeterminate form. So I think we can go ahead and apply L'Hopital's one more time. The derivative of 2k is 2. The derivative of e to the k is simply e to the k. And plugging infinity into this, we get the form 2 over infinity, which is equal to 0. So the test for divergence fails. So we'll go ahead and apply the next test on our list, the comparison test. Now, the comparison test states that if a sub n is less than or equal to b sub n, and b sub n is convergent, then a sub n is also convergent. But since here we can't get a form of this equation such that another equation is always greater than it, we're not going to apply the comparison test. So we're going to cross that off. Next test we'll look for is the alternating series test. And because this series is not alternating, which would require maybe another term here, maybe of minus 1 to the n. If we had this form in this equation, we could apply the alternating series, but since it's not alternating, we're not going to apply it. Next test we have is the ratio test. Now the ratio test states that the limit as n approaches infinity up to the value of a sub n plus 1 over a sub n. If the limit of this equation is less than 1, then the series is absolutely convergent. If the limit is greater than 1, then the series is divergent. I should say that would also include infinity, if it was infinity. And if the limit is equal to 1, then the test is inconclusive, and we have to use another type of test. So we'll go ahead and apply this test to this equation. So we'll say the limit as k approaches infinity of k plus 1 squared over e to the k plus 1, all divided by k squared over e to the k. And now we'll go ahead and rewrite this into a better form. We'll write the limit as k approaches infinity. We'll go ahead and multiply out this equation. So we'll get k squared plus 2k plus 1 divided by e to the k. And we know that e to the k plus 1 is simply e to the k times e to the 1. And then we'll go ahead and flip this fraction. We will get e to the k all over k squared. And immediately looking at this equation, we see we can go ahead and cross out e to the k. We see that we're left with a constant here, e. We can go ahead and write e out of the equation. And we'll go ahead and rewrite this again. We'll get 1 over e, the limit as k approaches infinity of k squared plus k plus 1 over k squared. And we see here we can actually write this in an easier form to understand once more. Dividing the denominator by each term of the numerator, we would get k squared divided by k squared plus k over k squared plus 1 over k squared. Taking the limit of this equation, we get 1 plus 1 over k plus 1 over k squared. And as infinity approaches k, these two will tend to 0. And we will get 1 over e times 1 plus 0 plus 0 is equal to 1 over e. And because the limit is less than 1, then we can conclude that the series is absolutely convergent. And that's pretty much the answer to the equation. So thank you for watching our video. If you like our video, please go ahead and check out the other videos that we have on some other questions from Stewart Calculus. And again, have a good one.